Adding more layers to a graph neural network can make it worse, not better. In stock networks, deep GNNs erase the very differences that matter. We'll show the math behind oversmoothing and why shallow models win. Here's the puzzle. In many machine learning tasks, deeper models capture more complex patterns. But in graph neural networks applied to finance, the opposite happens. Stacking layers makes all stock representations converge to the same point. This is oversmoothing, and it's a fundamental limit of the math, not a bug you can train away. A typical graph convolution layer updates each node's representation by averaging its neighbor's features. The formula shows this. H at the next layer equals an activation function applied to the normalized adjacency matrix times the current representations times a weight matrix. The normalized adjacency matrix is key, it's the symmetric version that keeps the math stable. As the number of layers goes to infinity, the normalized adjacency matrix raised to a high power converges to a projection matrix. This projection collapses all nodes in each connected component to the same value. So no matter how rich the initial features, deep stacking wipes them out. The speed of oversmoothing is governed by the spectral gap, which is 1 minus the second largest eigenvalue of the normalized adjacency matrix. A small spectral gap means the matrix quickly amplifies the largest eigenvector, which is the constant vector. So nodes become identical fast. Stock networks built from correlations, industry links, or supply chains are dense. Almost every stock is connected to many others. This density makes the spectral gap small, so oversmoothing kicks in after just 2 or 3 layers. That's why deep GNNs are not just unnecessary, they're actively harmful. The practical takeaway, a 2-layer GNN often beats a 10-layer one. The shallow model preserves local structure, while the deep model oversmooths. Many papers claim deep GNNs work, but they rely on tricks like residual connections or gating to delay the inevitable. Some architectures add residual connections or gating mechanisms to allow deeper networks. These tricks slow down oversmoothing, but they don't solve the root cause. The underlying Laplacian smoothing still pulls nodes together. So you're just delaying the inevitable, not changing the math. In quant finance, the graph's role is to inject an inductive bias, like industry factors or momentum spillover. You don't need infinite depth, you need the right structure. The graph tells the model which stocks are related, and that's a prior, not a deep hierarchy. Instead of stacking layers, we can use a diffusion-based approach like APPNP. It computes a personalized PageRank-like propagation that aggregates multi-hop neighbors in one step, while keeping a fraction of the original node features. This avoids oversmoothing by design. Another alternative is the Graph Attention Network, or GAT. Instead of fixed weights, GAT learns to weight each neighbor's contribution. This lets the model focus on the most relevant connections, preserving local information even when aggregating many hops. It's more flexible than a fixed convolution. So, the next time you're tempted to stack more GNN layers, remember, in finance, shallow is often better. The math of Laplacian smoothing guarantees oversmoothing, and the spectral gap tells you how fast. Use diffusion or attention to get multi-hop information without the depth. Thanks for watching. Markets reward discipline, not certainty. If this analysis helped, like the video and subscribe to DeepQuant. Tell us in the comments which market idea we should test next. Evidence beats noise. Control risk before chasing returns.